Welcome to this lecture number 10 of the course Computational Hydraulics. We are in module number 2 numerical methods, and in this particular lecture we will be covering unit 6 partial differential equation IBVP, that is initial boundary value problem. What is the learning objective for this particular unit? At the end of this lecture, students will be able to discretize the spatial and temporal derivatives of single valued multi-dimensional functions using finite difference approximations. Also, they will be able to derive the algebraic form using discretized partial differential equation, initial condition and boundary conditions. Let us consider our general equation. In our previous lecture, we have considered only this term and sourcing term for modeling the boundary value problem, where phi is the general variable, and in that case we have considered a two-dimensional system where this tensor is having 4 values or 2 directions. In this particular lecture, we will introduce another term which is the temporal term. So, we will have 2 spatial directions x, y and one temporal direction, that is t. So, with this information we can simplify this equation with temporal term, and we can write this lambda phi, let us consider that it is not varying with time. So, we can write it as coefficient del phi by del t, gamma x del 2 phi del x 2, gamma y del 2 phi del y 2, and this is again sourcing term, and this is valid for omega, that is for our interior domain of the problem. We are considering a two-dimensional system where on top we have Neumann condition, on bottom we have Neumann condition, and left we have Dirichlet, right we have Dirichlet kind of condition. With this information we can define the boundary condition. However, for initial boundary value problem, we need to specify the initial condition. This is two-dimensional in space. So, with this information we need to define this initial condition. Initial condition, that is valid for x, y within the domain, and this 0 is t equals to 0, that is initial time level. So, this phi naught is varying with x and y only. Boundary condition on left hand side, that is x is equal to 0, we have this phi 1, right hand side Lx y t phi 2, on top and bottom, this is at the bottom x for all x y is equal to 0, this value is 0. Again we have this x is equal x y is equal to L y, that is top boundary, we have specified value equals to 0. So, we have completely defined the problem with our governing equation, initial condition and boundary conditions. Now, we need to discretize this system with finite difference approximation. So, first of all, if you consider domain discretization, then we can define this Lx and Ly with del y and del x as space intervals in y and x directions. With this, for a general location I j, these are the neighboring points. That means I j minus 1, I minus 1 j, I plus 1 j, I j plus 1. With this, we need to introduce the temporal dimension. This is only spatial dimension discretization, and this is valid for boundary value problem, and in this case also we can utilize it. However, we need one extra dimension to discretize the IBVP problem. So, with extra dimension, we can define it on the another axis t. This is x, y, and this is our t direction, that is time direction. So, at each time level we need to discretize our domain in spatial directions. So, this is level n, this is level n plus 1, and we are in explicit scheme. What is this explicit? In explicit scheme, we are considering the spatial values for neighboring cells and the neighboring points or nodes, and the node for which we are discretizing at the present time level or nth level, and we consider only the n plus 1 level value for the central or the point which is under consideration. This is like inverted umbrella kind of situation, where we have this portion is considering the future time level value, and in inverted umbrella this portion is considering the present time level spatial discretization. With this information, if we start discretizing our governing equation, then we are discretizing at the present time level. So, that is why n I j, n is for time level, I j for x and y direction. So, all are at n I j level. This sourcing term we need to consider at n I j level. With this, if we discretize our temporal derivative, then we can see that this is forward difference in time, and we have discretization or truncation error of order delta t. In explicit scheme, the space derivatives are discretized at the present time level. So, now we need to consider the space derivatives, the 1, 2, these two derivatives are space derivatives. So, this should be discretized at the present time level or level n. So, space discretization for first del 2 phi by del x 2, we are considering phi I minus 1 j n to phi I j n and phi I plus 1 j n. So, we are only changing the index for I, keeping other indices constant. So, in this case we have second order accuracy for the truncation error in del x. If we consider the y direction, similarly we will have second order accuracy in y direction. Now, we can integrate all these derivatives to construct the discretized form of the governing equation. So, we have this lambda phi, gamma x, gamma y, these values are as coefficients. Interestingly, in this case n plus 1 level value is unknown, and whatever value is available at the present time step that are denoted with level n. So, we have only one term which is unknown. I have marked it with this cross, and for other terms values are known. In this case, we can see that overall truncation error for this scheme is del x square, del y square, because of two spatial derivatives, second order spatial derivatives for phi in x and y directions, and del t, this is coming from the temporal discretization of the time derivative. With this, if we start simplifying the equation, we can write it like this: only unknown term in the left hand side, others are known. So, we can write it in simplified form with this notation: alpha x, where alpha x is gamma x delta t, this lambda phi del x square, alpha y is gamma y del t lambda phi del y square. So, with this, if we write the right hand side, so we have all values known. So, now we can try to get the information about the future time level value with the available values of the present time level. If we use our single index notation, again we can transform this whole system into single index. With this, we can write it as phi L n plus 1, where this j minus 1 will be L m L minus m plus 1, I minus 1 j, that will be L minus 1, I j is L, I plus 1 j is L plus 1, L plus m plus 1 is for I j plus 1. So, with this information, again this is I j is L. So, with this information we can get the discretized form of our governing equation with single index notation. Now, we need to see how to get the solution with this explicit scheme. So, what are the standard steps for this explicit scheme? Because we need time stepping algorithm. What is this time stepping algorithm? In time stepping algorithm, we define the values with change in time in terms of our governing equation, and we write it in algorithm format. In this case, what are the things that are available? We have lambda phi, gamma x, gamma y, s phi, del x, del t, del y, del t, phi n at time step n. That means, we have n equals to 0. That means, initially we have initial condition available, and at the starting of any time level our phi n value is specified. So, with this what is the result required? In this case, we need updated value of n plus 1 at time n plus 1. Now, we can write this in algorithm format. This is for I j or lth point, and for any time level, to predict the future time level, we need to run this algorithm. That means, t less than n time do. So, first we need to solve the governing equation for interior points. For all interior points, we need to get the phi l n plus 1 level value with initial condition. Then we need to solve the boundary conditions at boundary value points, and then we need to update the time level to n plus 1 for calculation of the next time step or next time level value. So, this while loop or this do loop that will run until we reach our n time level. So, in this explicit scheme, important thing is that first we need to solve the interior points, then we need to get the information about the boundary points, that is sequentially, and then we need to update this time level from n to n plus 1. Now, let us consider implicit scheme. What is this implicit? In implicit scheme, we have n plus 1 level value, nth level value. So, nth level value we are utilizing only one point, that is the central point or central node. For others, we will be utilizing the future time level value, which is unknown. This is like a straight umbrella, and if we discretize our equation, we need to discretize it at future time level value, that is n plus 1, n plus 1. With this time discretization, this is backward in time, because we are considering this thing. Again, we have first order truncation error for time. Implicit scheme, space derivatives are discretized at the future time level n plus 1. So, Now, if you discretize the space derivatives del 2 phi del x 2, del 2 phi del y 2, we should discretize it at future time level. So, space derivatives, these are discretized at n plus 1 level. Similarly, for y direction. Now, we can write our governing equation in discretized form. In this case, only unknown thing is or known thing is n level values. Also, this S phi sourcing term that may be defined for a particular system. So, 1, 2, 3, 4, 5, 6, 7, these terms are unknown, although this phi I j n plus 1, if we combine with this term and this term, that will be counted as single term. So, we have 1, 2, 1, 2, 3, 4 and 5 unknown values for this particular governing equation. And overall accuracy of the scheme is del x square, del y square, in time this is del t. In compact form, again we can write it like this with alpha x and alpha y. In this case, these are unknown values 1, 2, 3, 4 and 5 unknown values, and right hand side we have known values available. With this information, we can construct the matrix form using a single index notation. For single index notation, again we need to convert it with L minus m plus 1, L minus 1, L plus 1, L plus m plus 1 format. In this case, these values are unknown. So, matrix form is essential for this problem. So, if you want to solve this implicit scheme, again we need to define the time stepping algorithm for this one. So, data for this one is lambda phi, gamma x, gamma y, S phi, del x, del t, del y and del t, phi n at time step n. So, with this, if we proceed, what result is required? Result is updated value of phi n plus 1 at time step n plus 1. In this case, we need to run the while loop t less than n time. In explicit scheme, we have observed that first we need to solve the interior points using a governing equation, then boundary points using boundary condition. In this case, we need to solve interior points and boundary points simultaneously. So, solve governing equation and boundary conditions in discretized form. So, simultaneously we need to solve the governing equation and boundary condition. Then we need to update the time level to get the future time level value or present time level value for the next time step. Now, we need to define the theta scheme. Theta scheme, we consider some intermediate time step. in that intermediate time step, first step is explicit in nature. Explicit means we are defining at nth level. Then we define our implicit step. Implicit step is defined at n plus 1 level. So, with this we can write the explicit step for n plus theta level. Right hand side all values are known at nth time level, and implicit step we have all unknown at n plus 1 level, and n plus theta is known from the first step. If we combine these two steps, then we can write it as I j n plus 1 minus phi I j n, and this is some kind of weighted average theta 1 minus theta for x direction, again theta 1 minus theta for y direction. In this case, an important point is what will be the truncation error order for del t or time. If we write it for explicit step, it is in terms of n plus theta, we can write it. Again for implicit step, we can write it for n plus theta, and if we combine these two, we can get the time derivative here, and interestingly this is del phi del t, this is at n plus theta level, and we have this 1 minus theta square term. Now, if we consider that theta equals to 0.5, obviously this term will be 0, and truncation error of the scheme will be of the order del x square, del y square, del t square. Essentially in this case we are getting second order accuracy in time. The scheme is known as Crank-Nicolson scheme. If we see the space time discretization for Crank-Nicolson, it is the combination of explicit scheme and implicit scheme. This is n plus half level because theta equals to half, and first step is inverted umbrella and second step is with straight umbrella. With this we can discretize our governing equation and we can solve using Crank-Nicolson scheme. In Crank-Nicolson scheme, if we see our governing equation in discretized form, that is actually can be solved using the implicit algorithm that we have discussed, because in Crank-Nicolson scheme we have unknown values available on the left hand side and right hand side also. Thank you.